Just to pick up where we left off yesterday, we had the paleontologist, and it was trying to figure out how old the bone was by using carbon-14 dating. Um, we are on the last part right here. It says the growth factor is 1 plus R, and the decay factor is 1 minus R. We know that. Well, that's from the form way up here. Okay, 1 plus R is the base. The base is your growth factor. 1 minus R is the base. That's your growth decay factor. Sorry, decay factor. So when we have an equation in the form, when we have an equation in the form y equals e to the ct, the e to the c part is equal to either 1 plus r if it's growth, or it's e to the c equals 1 minus r if it's decay. So for our problem here, since it was exponential decay, and the reason we know it's decay is because there's a negative exponent, because e itself is a growth function, remember. E to the x looks like this. We memorized that. So if you put a negative in front of the exponent, what that does is it reflects it across the y-axis, and that's what makes it decay. Okay? So here's what we're going to do. We're going to find the decay factor. So the decay factor, not the decay rate, but the decay factor equals, what was our equation? E to the, there were 3 zeros and then a 12. So e to the negative 0.00012. Oh, hey, Blackstone. And that equals 1 minus r. Yeah.
Do you know, I've heard that Miss Helen's class is in this hallway. Do you know what room?
I actually
Have
don't.
you seen Miss Helen?
I don't know what she looks like. I'm sorry. Has anyone seen Miss Hillman up here, like in between class? Oh, that's Miss Hillman right across the hall? Okay, yeah, there you go. Thank you. I'm sorry, I recognize her, and I know Miss Hillman's name, but I hadn't put two to two together. That's Miss Hillman. She's groovy. She dances in between classes like I do, so she would fit up here well. So I take the part without the t from the equation, e to the negative 0.00012. Get rid of the t, and because it's decay, I set it equal to 1 minus r. Now all I got to do is solve for r. So to solve for r, let's see, I'm going to add r to both sides, and I'm going to subtract e to the negative 0.012. So these two guys right here essentially switch places. So I get r equals 1 minus e to the negative 0.00012.
Sorry.
No, that's fine. Go ahead and type that into your calculator and see what you get.
On this one, the straight rate says 6 girls.
Yeah,
6 boys.
I changed it. I changed
You're
it from
doing
prep.
eight.
Yeah. I figured, yeah, because I don't want it to be mixed. So like a girl is trying to pull. I mean, we can do whatever we want. I want it to be mixed, but I don't want girls to have to pull a big heavy guy. You know what I mean?
Yeah.
So the way I have it here is just the boys will pull and all the girls will ride.
Okay.
But they can mix it up if they want. So
Okay. I
that's
just need to
why.
change my.
That's why I said. Do you think that'll work? Just
I
have the
think it
guys
will.
pull and the girls ride.
Just kind of yeah. I mean, we could do
There
that.
might be a girl who wants to
There's
pull.
always some girls that want to pull.
Yeah, that's why I originally had it preferably 6 and 6.
Yeah.
But I want it to be mixed. So I don't know how to say that, but still give them the opportunity to have girls pull.
I mean, I just think so you figure it out.
Figure it
I
out.
think it's kind of funny when you have a guy going and a girl that can't keep
So you want to put it back to 6 and 6?
I mean, I don't know. It's whatever you want to do. The wristbands say 6 and 6. So
Okay.
I can cross out a B and put a.
Well, no. Let's just do 6 and 6 and make it funny.
I mean, it's always that way.
Yeah.
Right?
Yeah. Okay, I'll change it back to 6 and 6 during lunch. Yeah.
Well, I can do it. 'Cause I haven't pulled up.
Oh, you
It's the
do?
only thing that's on, right?
Yeah. And then I have to copy and paste it into the Canvas
Well,
thing.
I mean, it's already in Canvas. Do you just want to keep it 8 and 4?
No, because it wasn't Canvas like the other way at first.
Okay.
Let's just change it back. I don't think anyone's
It's
seen
kind
it
of
since
a
yesterday.
smart, I don't know. It's kind of funny.
When it's 6 and 6.
And it's funny when people aren't smart about it and they do a big guy and a girl's carrying him.
Okay, let's do 6
Like,
and
it kinda
6.
gives
I
you
agree.
more-
I agree.
Okay.
Let's do 6 and 6. Okay, let me catch up with y'all. So 1 minus second ln to the negative 0.00012. We get r equals. Now, what does that number mean? That means that it's 0 and then 1, 2, 3 zeros and then a 1, 1, 9. This is your decay factor. Now it's as a decimal. How do I change the decimal to a percentage? Move it 2 units to the right. So point zero, bless you, 1199%. So it's a very, very small percentage. If you think that it takes 57, almost 6,000 years for this to lose half of its mass, the decay factor is very, very small. It only loses 0.1199% of its mass every single year. Okay? If this were a growth function, you would have said e to the c equal to 1 plus r, and then solve for r. So that concludes question number 2. Any questions on the bone? The paleontologist question. All right, let's move on so y'all can get to working on this. Y'all have all day tomorrow, by the way, to work on this. The way this is going to work, all day tomorrow to work on this. We'll review all of Chapter 13 on Thursday, and then we'll quiz over all of Chapter 13 on Friday. Got it? Okay. So we're going to do exponential regression now, right? So the total catch in tons for Iceland's fisheries from 2012 or 2 to 2010 is shown in the table. Let X, oh, look at this. This is important. Let X represent the years after 2012. So if I make a new X column here, after 2002, sorry, I'm going to let 0 be 2002. How many years after 2002 is 2002? 0 years. So we're going to renumber everything 0, 1, 2, 3, 4, 5, 6, 7, 8, so on and so forth, because it represents the years after 2002. So that year 2002 becomes our basis. F of X represents the catch in millions of tons. Wow. So 2.145 millions of tons all the way down to 1.063. Now, what do you notice about the tonnage of fishing that takes place? It's decreasing, isn't it? Is that because they're fishing less, or are there fewer fish to catch? We don't know. But that's kind of what maybe scientists would like to study. They see trends that happen naturally, and they try to figure out what the reason is. All right, so remember how to do this? We go to Stat. We hit the Stat button. We hit Edit, which is Enter, because it's automatically on Edit. And you should see your L1 and L2 columns. So in L1, we're going to type our X values, which are years past 2002. So 0, 1, 2, 3, 4, 5, 6, 7, 8. And now the fun part, the part that I hate the most, typing in data, okay? So get 2.145, 2.002, 1.750, 1.661, 1.345, 1.421, 1.307, la-di-da, 1.164, and finally 1.063. Now, when you look here, you should have double check, make sure you typed it in correctly. You can miss a decimal or something like that. You also can miss a number because you didn't hit enter. You should have ordered pairs all the way across. All right, now what I'm going to do is I'm going to go to y equals. I'm going to click up to plot 1, and I'm going to highlight it by hitting enter. That turns on plot 1. Now, with the data in the stat table and plot 1 turned on, I want to see the data points. So I'm going to graph it by hitting zoom what? Do you remember? Zoom 9, that's zoom stat. And now you see the points like that. Now, what you want to do is, one of those points looks off, but maybe that's just how it is. That looks almost like a linear regression, doesn't it? If you were to look at that, it looks like you could draw a straight line through it. So a linear regression might be a good fit. This one tells us to do an exponential regression. So it could also be an exponential decay. So to do an exponential regression, we go to stat, like we did before. We click to the right to calculate now. And we go down and we choose our menu. We've done quadratic regression this year. We've done linear regression this year. We've done cubic regression. I don't know if we've done quartic. There's another linear regression. That's natural log regression. We can skip past that. Go down to 0. It says exponential regression abbreviated, expreg. That's exponential regression. So we're going to choose that one. And then it says, is your X list L1? Is that our X's in L1? Yep. So we hit enter. Is your Y value in L2? Yep. You can skip the frequency list. This is the important one. We want to send the equation that it calculates to Y1. So we're going to put alpha trace, that's accessing the Y's, alpha trace, and we're going to select Y1. Click calculate, and it'll highlight it. It's blinking. It's ready to go. Like the sophomores were yesterday at the start of the Powder Puff game. They're blinking, ready to go. And then we hit enter, and it gives us the variables for A, B in that format. Now, we don't really care to type that in by hand. So if you go to y equals, you'll see that it's already in there. So really now we just hit graph, and you'll see the best fit line go through it. So it almost looks linear, but it looks kind of like it's bent, right? Like you had your phone in your back pocket and you kind of sat down and your phone bent a little bit, right? It's got a slight curve to it. Still works, right? But it's got a slight curve to it. So that looks like it could be a pretty good fit for exponential. Not just linear, but exponential. Okay? So that's how we get the equation. Now we answer the question here. If this pattern continues, let's call this f of x. So we got f of x. If this pattern continues, in what year will the total catch fall between 500,000 tons? 500,000 tons. All right, so what I want to know is, first of all, what am I trying to find? I'm trying to find the year, which is the x value. So I need to find x. I don't know x, but I know the y value. I know f of x. It needs to be 500,000 tons. So if we're measuring the y values in millions of tons, I want to know when f of x equals what number? What do I set it equal to? Half. I set it equal to a half or 0.5, either one. Now, if you notice, when the table ends, we're at 1 ton. It's going to continue to drop possibly according to this pattern, and it'll be down to 0 someday. But I want to know right now where it's equal to a half. So this is where I set it equal to a half. I go to y2 and I type in a half. And then I hit graph and I look for the what? I look for the point of intersection. Do I see it? No, because my window, if you go to the window, since it only used the data points, the lowest y value on there is 0.879. You see that? When you go to the window, it says the minimum is 0.879. I want to know when it's equal to 0.5. So I'm going to come down here to the y min, and I'm going to change it to 0. I might as well just see the x-axis. All right, now I'm going to hit graph, and now I see the line. That's better. I see the red line. But now it looks like they intersect off the screen, don't they? So now I need to go out a little further to the right. So I go to my x max, and instead of 8.8, I'm going to go out to 20. I'm just going to go out to 20 years, and I'll hit graph. Now, if that still didn't work, I would go up more and more and more until you can see them intersecting on your screen. So I've got it, right? So now I just got to find the point of intersection and write down the x value. So second trace number 5, enter, enter, enter. And you get 16.745 years. Now remember, that's years after what year to start with? Years after 2002. The question asked you in what year. It didn't ask you how many years after 2002. It said in what year. So the year then would be what? I'll say in year what? 2018.745, right? Which is really in what year? 2019. That's the trick to this question. 2018 has already come and gone, and we're already 3/4 of the way into the next year. What's the next year after 2018? 2019. So that's the answer. It takes place in 2019. January, February, March, April, May, June, July, in September. Sometime in September. In September of 2019. Boy, I wonder if that's the case. It's 2024. I wonder if they're still doing any fishing at all up there in Iceland. You think they are? I don't know. Iceland's the one that's pretty, right? And Greenland's the one that's icy? That was a clever trick. You got to admit that. That was a good trick that the Vikings did. All right, any questions on how to do that problem? We've done regression all year long. The only difference is now we're using exponential. And you use your calculator as a tool, like the fishermen seek out the fish. You're seeking out on your calculator the point of intersection. Okay, you're changing the windows, y min, x max, whatever, until you see it. All right, so remember when I just graphed these points right here, I said it almost looked like it could be linear. Okay, one of the things that you do in statistics, if you go on to take on-ramp statistics, is you'll have to plot points, and part of what you do is you decide, is it linear, is it quadratic, is it exponential? And there are several different ways that you'll learn in statistics how to figure that out. One of them is called eyeball test. You look at it and say, hey, does it look like it's a good fit? Another one is what's called, you calculate the residuals and you look at the residual plot. If you still see a pattern in what's called the residual plot, you haven't captured all the variability. You can just use that term. It's plugged in. All right, so here's what we want to do on example 4. I'm going to be given a scatter plot, look, and I want to know if it's going to be linear, I want to know if it's quadratic, and I want to know if it's exponential. If it's linear, I want to know if the slope is negative or positive. We call that a correlation. A negative slope means negative correlation. A positive slope means positive correlation. You don't need to know that at this level, but that's a statistics term. If it's quadratic, you want to know if the leading coefficient is positive or negative, right? If it's negative, it's going to open down. If it's positive, it's going to open up. And if it's exponential, we want to know if it's going to be growth or decay, if the base is between 0 and 1 or greater than 1. Got it? All right, so let's look at the first one here. We got miles per gallon and years since 1996. I don't know what this represents. It doesn't really tell us. But we're graphing miles per gallon against time. Does it look linear, first of all? Could a line describe the best fit like that? That's not bad, right? But it doesn't seem like it's the best fit. Okay? Does it look like it could be exponential? Oops. When you hold it too long, it curves. I forgot. Does it look like it could be exponential? Maybe, right? And if so, it'd be exponential what? Growth or decay? Growth. But could it be quadratic? A quadratic foot actually looks a little better, doesn't it? I think, because notice you have points that start off high and then they come down and reach a low point somewhere in here and then they start going back up again. You see that? So by the eyeball test, they all three could work, absolutely could work. And it turns out the data could actually come from any one of the three. But based upon the observations that we've collected, I would say that a quadratic would be the best fit for this one. And since it opens up, is the leading coefficient positive or negative? Positive. The leading coefficient is greater than 0. I'll just leave it like that. All right, so it's a subtle difference, right, between the exponential growth and the quadratic. It's subtle, but I think it's there. I'm not just seeing things, right? Do y'all see it kind of coming down too before it goes up? Yeah. All right, good. All right. Oh my gosh, this was so easy. This is a quadratic, right? What? Does it look exponential? Oh, it looks. That was a joke. Okay, yeah, you're making a joke like I am. You can pretty much almost connect the dots on this one and make it what? Linear. Yeah. So is this a positive correlation or a negative correlation? Positive. I'm going to use the term positive correlation. That just means that there's a positive correlation between the year since 1990 and the bald eagles in Paris. No, bald eagle pairs. Oh, I'm reading that wrong. I thought it was bald eagles flying around Paris, France. I should have no. See, this is why you have to spot for me, Caden. You need to come spot me over here. What does that say? I can't even read it. Bald eagles in Paris, right? Yeah, in the lower 48 states. So there's a positive. That's good, right? If you're a bald eagle, your family's growing, or if you're a true American, you like bald eagles, don't you? It's our national. It's our national food dish, right? Fried eagle. Kentucky Fried Eagle. KFE. Get you some. No, they're thriving. They're starting to come back. All right. What about this one? What would you guess on this one? Exponential would look like that. Linear would look like that. But it looks like also like it's dipping down and then going up, which would be what? Again, quadratic with a positive leading coefficient. All right. All right. Now, what about this one? Does this one look quadratic? Does it look linear? Does it look exponential? Yeah, this one looks like exponential decay. Exponential decay, which means the base is between 0 and 1. And that's it. Yeah. There have been fewer rear-wheel drive vehicles since 1977, which means that the vehicles are either front-wheel drive or all-wheel drive. Okay? They used to be rear-wheel drive, but now they've discovered that through a slide, rear-wheel drive vehicles are more dangerous. If you start to slide, the front wheels kind of steer you where you need to go. All right, we're done. Any comments or questions? Anyone had fried eagle? I think it's illegal in the United States. You got to go to Peru to eat it. You know it's illegal to own a bald eagle too? Like if one flies in your backyard and you train it to stay at your house, that's against the law. You're supposed to let them be free. Yeah, if it doesn't want to be free. What if you pick a bluebonnet in your backyard? Is that illegal?
No, because
It's on your property. That's right. Yeah. But if it's on the side of the highway, that's illegal. Yeah. What if you kill a rattlesnake while you're sitting in the bluebonnets on the side of the highway to take those nice spring pictures? Is that legal to kill a rattlesnake before it bites you? Yes, that's legal. Just be careful when you take those bluebonnet pics. Rattlesnakes love bluebonnet pictures too. All right.